This video explores the topic of linear and angular position measurements with encoders in Industry 5.0 within the framework of the European project titled Personalized Education in Measurement Science and Technology, Empowered by Machine Learning. Modern sensors and measuring transducers utilize advanced technologies to enhance their performance, accuracy, and reliability. They play a critical role in modern manufacturing systems, enabling precise monitoring, control, and automation of industrial processes. By providing real-time data, these devices help optimize efficiency, reduce downtime, and improve product quality. Position encoders are an important group of sensors necessary for the functioning of modern motion control systems. A position encoder is a measuring transducer that provides a digital output for a linear or angular displacement. The method of controlling the motor rotation by detecting the motor rotation speed and rotation angle using a position encoder is called the feedback control closed-loop method. Modern position encoders should feature an electronic identification label that enables automatic installation and system configuration. They provide online diagnostics, storage of operating data, and mobile access to status information, increasing reliability and simplifying maintenance. Together with additional sensor data, they enable data acquisition, condition monitoring, and predictive maintenance. Depending on the technology used, 4 types are distinguished: mechanical, optical, magnetic, and electromagnetic induction. The figure shows the optical encoder composed of a light-emitting diode, LED, photosensors, and a disc, code wheel, with slits holes in the radial direction, and it detects rotational position information as an optical pulse signal. Magnetic encoders use sensors to identify changes in magnetic fields from a rotating magnetized wheel or ring. Inductive encoders have charged coils that are passed over by a passive disc, modulating what charges the sensor receives. A linear encoder, also called a linear scale, consists of a scale that serves as a ruler and a head that detects position information. As with the rotary encoder, there are 2 detection methods: an optical method that uses light reflection, and a magnetic method that uses magnetism. Resolvers are robust angle transducers suited to application in harsh environments and have been used for decades in positioning applications such as tanks, aircraft, satellite antennas, radars, brake-by-wire, etc. The resolver is a rotary transformer, usually with an armature on the rotating shaft and 2 stator windings, which are placed at right angles to one another. The coefficient of coupling between their rotor and stator windings depends on the mechanical angle of the shaft. Resolvers and encoders are both devices that measure the rotary position of a shaft by converting mechanical motion into an electrical signal. The advantages that resolvers offer over encoders make them better suited for extremely harsh applications, such as military and aerospace equipment. One of the most significant benefits of resolvers is their lack of sensitive optics, which allows them to withstand much higher vibrations and shock loads than encoders. They are also resistant to electrical disturbances. From a performance standpoint, encoders have a lower weight and rotational inertia than resolvers, making them more suitable for applications with high acceleration and deceleration rates. Another advantage that makes encoders a more attractive option is that they can be upgraded by replacing the feedback element and changing software, whereas changing a resolver would potentially require a change in the converter, filter, supply voltage, and frequency. Position encoders are widely used. There are numerous applications, such as in automotive manufacturing, intelligent robots, aerospace, radar systems, machine positioning, printers, mechanical arms, machine health monitoring, CNC, computer numerical control, machines, integrated circuits manufacturing, crane positioning, industrial motor shaft positioning, scanners, telescopes, process lines, and elevators. If you're looking for extreme accuracy or working with highly dynamic motion, optical encoders are a good choice. Examples of these kinds of applications include pick-and-place robots, telescopes, antennas, and machine tool applications. Magnetic encoders are good for commodity-type projects, where several of the same encoders are installed. Mining operations are a good example, where vibration goes beyond 30 or 40 gigaseconds. Inductive encoders combine the contamination and vibration insensitivity of magnetic with higher accuracy that approaches the level of optical solutions. They fit nicely in general automation systems and work well with different types of servo motors, medical applications like CT scanners, and in the robotics industry. Optical encoders have the advantages of high accuracy, resolution, and cost performance, fine repeatability, and low environmental sensitivity. Therefore, they are widely used in accurate displacement measurement and motion control technologies, such as computer numerical control machines, robotics, precision motion control systems, fault diagnosis systems, etc. Using different measurement methods, they can be divided into absolute and incremental optical encoders. An incremental optical encoder, shown in the left diagram of the figure, consists of a disk divided into alternating transparent and opaque sectors. An absolute optical encoder's disk with n-bit resolution is divided into 2 to the power of n sectors, and each sector is further segmented radially into opaque and transparent sections. The figure is given for a 5-bit resolution. The figure shows a comparison between absolute and incremental position encoders. An incremental encoder is easy to manufacture and cost-effective for customers, while also being able to determine the speed and direction of motion. However, since all marks in a row are identical, it requires setting a reference point for position determination. Additionally, position information is lost when the electrical power supply is interrupted. An absolute encoder determines the exact angular position without requiring a reference point, and it retains position information even if the power supply is lost. However, it is more complex and expensive to manufacture, which results in a higher overall price. To manufacture an incremental encoder, a pattern disk is produced. This pattern separates the disk into clearly defined sections, often using alternating opaque lines and transparent windows printed on a clear surface. When an LED shines light onto the disk, the beam either passes through a transparent window or is blocked by an opaque line. Light that passes through reaches a photosensor positioned on the opposite side, while blocked light does not. As the disk turns, the encoder's channel A generates a sequence of high and low signals, depending on whether the photosensor detects light high or no light low. The number of lines on a disk is always related to the resolution. Typical values range from low numbers like 32 or 64 to much higher resolutions of 5,000 or 10,000 and beyond. The following picture shows several encoder disks. Lower resolutions are on the left and higher resolutions are on the right. An incremental encoder creates 2 pulse trains, A and B, as the encoder shaft rotates a code wheel. The code wheel could be an opaque material with slots, or a transparent material, glass or plastic, with opaque lines. The relative phase of the A and B pulses determines whether the encoder is rotating clockwise or counterclockwise. Absolute encoders operate differently. They output a unique code for each position on the disk. Each code is absolute, which means that since it is unlike any other code on the disk, it specifies a unique absolute position on the disk. The next drawing shows a disk for a traditional absolute encoder. It has 4 tracks and an LED array with sensors that read the pattern from each track. The incremental method has only 1 row of slits, while the absolute method has multiple rows. For example, if there are 4 rows of slits, you can find the absolute position of 16 angles from 0000 to 1111 in binary code, binary number. If there are 5 rows of slits, there are 32 patterns from 00000 to 11111. By doubling the row of slits to 8, you can see the absolute positions of 256 different angles. As the number of rows of slits increases, the resolution of the angle change increases, allowing for a finer representation of the amount of movement. For sector encoding, either natural binary code or gray code can be used. The main characteristic of gray code is that any 2 adjacent code words differ by only 1 bit. Gray code is used instead of natural binary code to minimize reading errors at the boundaries between sectors. Pseudorandom absolute position encoders are an advanced type of encoders that use pseudorandom code words inscribed longitudinally along a single code track on the code disk to encode angular sectors. These code words are part of a pseudorandom binary sequence of maximum length, known as an M sequence. Thus, the pseudorandom encoder design, which includes a single code track and 1 reading head regardless of resolution, maintains low complexity even as resolution increases. This simplifies the implementation of high-resolution encoders, which is their primary advantage. Additionally, Pseudorandom encoders enhance reliability by enabling the implementation of error detection methods and allow for direct zero-position adjustment after the code disk is mounted on the shaft. However, a notable challenge arises from the incompatibility of pseudorandom code words with conventional digital electronics, necessitating their conversion into natural binary code. Pseudorandom absolute position encoders, also known on the market as virtual absolute encoders, are available as rotary or linear encoders in both self-contained and modular configurations. Resolutions of these encoders are around 19 bits for 2 inches disk diameter and 20 bits for 3.5 inches disk diameter. An important component of an n-bit pseudorandom absolute position encoder is the code disk, which can be made from different materials, glass, mylar film, or metal, and it is affixed to the rotating system whose angular position is being measured. The code disk is divided into 2^n-1 angular sectors, each corresponding to a unique n-bit pseudorandom code. The angular position is measured relative to some 0 reference sector, encoded with a reference code word. Along the code track on the encoder disk is a synchronization track that defines the moment of reading a bit from the pseudorandom code track. It is also used to determine the direction of rotation and can be used in some hybrid encoder operating modes when determining position. Main characteristics of pseudorandom position encoders are 1 code track with pseudorandom code, 1 synchronization track, n adjacent bits define a unique code word, required conversion of pseudorandom to natural code, application of error detection methods for code reading, easier mounting on the motor shaft, and smaller dimensions of the encoder disk. A pseudorandom binary sequence of maximum length, known as an M sequence, with a resolution of n, is a cyclic binary sequence. It is generated by an n-bit linear shift register comprising ND-type flip-flops with a feedback branch, figure A. Bits of a pseudorandom binary sequence are obtained at the output of the last flip-flop. An all-zero state is not allowed. If it were, the shift register would never be able to exit that state. Pseudorandom binary sequence generation starts from an initial reference state of the shift register. With each clock cycle, the shift register moves to a new state, producing 1 pseudorandom binary sequence bit until it completes all possible states and returns to the reference state. Each n-tuple of consecutive pseudorandom binary sequences forms a unique code word, with a total of 2 to the power of n minus different n-bit code words within 1 PRBS period. Each code word is equal to a distinct state of the shift register. Inputs of flip-flops are obtained directly from the outputs of the previous flip-flops, while the input to flip-flop 1 is derived as a linear combination of flip-flops outputs generated by the feedback branch, comprising XOR logic gates implementing modulo 2 summation. The structure of the feedback branch, including the number and position of XOR logic gates, is pivotal for the design of the pseudorandom binary sequence generator. The feedback branch structure for a shift register of length n, producing the maximum length pseudorandom binary sequence, is determined by binary coefficients of the primitive generator polynomial. For each direct maximum length pseudorandom binary sequence, a corresponding inverse mirror sequence exists, which is essential for implementing the serial Fibonacci code converter. The inverse PRBS generator, shown in figure A, uses a similar n-bit shift register, but differs in that feedback connections follow reversed polynomial coefficients, and PRBS bits are taken from the input of flip-flop 1. Both generators start from the same reference state, but in the inverse generator, bits are loaded in reverse order. A key property of the inverse PRBS generator is that it traverses all 2 to the power of n-1 states in reverse order relative to the direct generator. After completing 1 full PRBS period, 63 states for n equals 6, both generators return to the reference state, marking the start of a new sequence cycle. An example of an inverse PRBS generator for resolution n equals 6 is shown in figure B. Since 2 consecutive pseudorandom code words in an M sequence differ by only 1 bit, detecting only that bit is required, with the rest inferred from the previous code word, allowing the use of a single reading head. There are 2 different serial readings of the pseudorandom code. Serial reading with 1 code reading head has the disadvantage of no continuity in the formation of code words when changing the direction of rotation. It is shown how a read bit is loaded in the shift register for different rotation directions and for a 5-bit pseudorandom code. Serial reading with 2 code reading heads has advantages in continuity of code word formation, and it is a reliable method of checking code reading errors. The disadvantage is the small and fixed distance between the code reading heads, which can cause problems. It is shown how read bits are loaded in a shift register for different rotation directions and for a 5-bit pseudorandom code. The first way of error detection is actually a well-known test that can be applied to any incremental encoder, where the synchronization track signals from the encoder are inspected for a disallowed quadrature sequence. Quadrature square waves are 2 square waves that are phase-shifted with respect to each other by 90 degrees electrically. The quadrature pair may be thought of as being a series of 2-digit binary numbers, also given decimal state names for convenience below. 4 groups of state transitions are possible, depending on the direction of encoder motion. The figure below shows the digital quadrature square waves, binary representations, and state diagrams for each of the 4 quadrature state transition groups. The state diagrams show how a rapidly sampled pair of square waves is perceived to change from state to state by the decoder. Forward and reverse motion are self-explanatory. The no change group shows how the states are perceived not to have changed within a sampling period. The error group illustrates illegal state transitions, those with simultaneous edges, or edges close enough to fall within the same sampling period. Possible causes of an illegal quadrature sequence include incorrect or shortened wiring from the encoder read head, damaged disk or scale, or overwhelming noise interference. Reliable method of error detection can be applied at pseudorandom position encoders when the pseudorandom code is read by 2 code reading heads. A fixed distance between the reading heads is used as a reference for checking the correctness of the read bit from the pseudorandom code track. That is, in this bit checking procedure, one code reading head forms the main code word, register X, while at the same time the other code reading head forms the control code word, register Y. When a serial pseudo-random to natural code converter is applied, the main code word is loaded into the Fibonacci generator register, and the control code word is used instead of the reference code word. The resulting distance between the main and control code words should correspond to the physical distance between the code reading heads. This is a very reliable method of detecting code reading errors that provides us with information about the correctness of the read code and thus the accuracy of the position information. When mounting the encoder on the motor shaft, it is necessary to apply a reliable zero position adjustment procedure that allows for the highest accuracy in order to later have a higher accuracy of the measured angular position value. Due to the properties of the pseudorandom binary sequence, any code word that coincides with the zero position of the motor shaft can be accepted as a reference code word. One solution for setting the zero position of a pseudorandom encoder is to have a button on the encoder housing, where pressing it starts the process of reading a code word that will be accepted as a reference code word and will be stored in the appropriate flash or EEPROM memory of the encoder. The stored code word is used in the pseudorandom encoder operation algorithm as a reference code word, with respect to which the serial conversion of the read code word is performed. Before storing the code word as a reference, a check can be made on the reading of n or more subsequent bits. If an error occurs in reading a bit, the procedure must be repeated. This avoids any use of a correction factor that would be added or subtracted from the currently measured position value, which increases the position determination time. This procedure speeds up and automates the process of setting the zero position when mounting a pseudorandom absolute encoder on the motor shaft. As digital electronics cannot process pseudorandom code words directly, the read-in bit code word requires conversion into the natural binary code. The serial pseudorandom/natural code converter is one of the most widely utilized methods for converting pseudorandom code into natural binary code. It operates on the principle that each direct PRBS has a corresponding inverse PRBS. The inverse PRBS generator, which produces the inverse PRBS relative to the PRBS encoded on the code disk, is at the core of the serial code converter. The read code word is entered into the in-bit shift register of the inverse PRBS generator within the code converter. The shift register transitions to a new state at each clock cycle, traversing states in reverse order compared to the direct PRBS generator, thereby approaching the reference state. When the shift register reaches the reference state, the code conversion is completed. The serial code converter incorporates an n-bit counter that counts clock cycles from the start of the conversion. The output of the counter, at the moment when the shift register reaches the reference state, represents the distance between the read code word and the reference code word. Position encoders are electromechanical sensors attached to motors that convert rotational motion into electrical signals, digital or analog, to provide real-time feedback on position, speed, and direction. Position encoders can be classified into several types according to the detection method: mechanical, optical, magnetic, electromagnetic induction, and capacitive. When choosing an encoder, you should pay attention to its characteristics: resolution, accuracy, repeatability, safety, interface, size, and rotation speed. Additional features of encoders can be self-calibration, zeroing, single-turn, or multi-turn, etc. Encoders are key to achieving precise, repeatable motion in modern automation. Whether you're controlling speed, position, or both, understanding the differences between encoder types and how they integrate with your drive platform helps ensure your system performs at its best. New trends in encoder technology are: the integration of nanotechnology into encoder design is an emerging trend, offering the potential for higher resolution, enhanced reliability, and durability. Nanoscale components can provide more precise measurements and contribute to the miniaturization of encoder systems. Wireless technology can provide remote monitoring and control of the encoder. Wireless-enabled encoders can be used in scenarios where wired connections are impractical or challenging. In some applications, encoders must be designed to withstand harsh environmental conditions, including extreme temperatures, vibrations, and contaminants. This trend ensures the reliability and longevity of optical encoders in diverse industrial settings. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš, and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.